Okay, now it's recording. Okay, so like we said, measuring magnetic fields is difficult, so if we can relate the magnetic field to the current in a unified manner and relate specifically the change in magnetic field to the change in current, then we can more easily calculate the EMF that is induced. And this would be, for example, a back EMF. So you connect an inductor to a 9-volt power supply and you turn on that 9-volt power supply. It is not going to go from 0 to max current in 0 amounts of time. It will take a certain amount of time for that inductor to have the current ramp up to full strength. And the reason is as the current changes inside of the inductor, it changes the magnetic field within the inductor, which causes a back EMF. Basically, it's akin to mass. So if you imagine going and pushing on an object, the more mass that you have, the more difficult it is to change that mass's velocity. And if you have more inductance, the more difficult it is to change the current within the inductor. So for a solenoid, what we do is we can go through and actually measure what the inductance is, and we already showed this last time, but the inductance is going to be on the order of number of turns squared. So big N is number of turns, and little n is number of turns per unit length. So if you can go from 100 turns to 200 turns, you can up your inductance by a factor of 4. It's going to be more massive in an electrical sense, meaning that it is more difficult to change its current as a function of N squared. And so you can imagine that this is something that we can either be frustrated by or make use of in terms of electrical engineering circuit design. If you want the current to change very slowly, you would need to have an inductor with very high inductance, and if you wanted it to be very quick, you would want to make sure to minimize the inductance in your circuit. And we also said that if we want to measure the change in magnetic field inside one inductor to figure out what the EMF in an alternative inductor would be, well, then we can still go back through and say that the change in magnetic field comes from the change in current. And you can see that the mutual inductance, for example, between two solenoids that are embedded within one another is going to be mu naught times the number of turns per length in the inner and outer solenoid, respectively, times the length of the two solenoids, assuming those are the same length, times the area of the inner solenoid. And so I want to get back to the idea that we talked about with capacitance. With capacitance, one of the things that we said is capacitance is defined as Q over V, but capacitance does not change based on Q or V. It's a ratio that always holds constant. It's more or less the same thing here. Inductance is not changed by how much current you have flowing through it. You always end up dividing by the current, and so it is current independent. Inductance is current independent. If you know what the inductance is for 1 amp and you ramp up your current to 2 amps, you still have the exact same inductance. And with this, you can work with the idea of inductance, you can work with the idea of magnetic fields, and the idea is if it takes energy to change the current state inside of an inductor, either to cause it to ramp up or to ramp down, then that means that there is energy associated, a kinetic energy, if you will, associated with the system. Again, kinetic energy is measured as 1/2 mv squared. Here we've said that L, the inductance, is a measure of electrical inertia inside of your circuit. So we've got 1/2 times inertia, mass, inductance, times velocity, which is the movement of charge, so current squared. So we have that the energy stored inside of an inductor is equal to 1/2 Li squared. And if you look in your book, then what you will find in your book is that, okay, if we think about 1/2 Li squared and convert this back to magnetic field strength, and I think this is proven to you in your book using a solenoid, I've left out the derivation here, then for any given magnetic field, the energy associated with that magnetic field is equal to B squared over 2 mu naught. B squared over 2 mu naught, which is not unlike the energy stored in an electric field, which was E squared over 2 epsilon naught. So there is energy stored in magnetic field. Or another way to think about it is there is energy required to change the state of a magnetic field. This is true if you're an electrical engineer, but I just came from a meeting where we were talking about magnetic squeezing, if you will, of filaments inside of galaxy clusters. This is present everywhere, that there is a certain amount of energy associated with the magnetic field, that when you try to squeeze the magnetic field together, there's a certain amount of energy required to go into that physical squeezing, and you end up getting that to change that, you have to put work into it, whether by thermodynamics or fluid dynamics or something else. Yeah, even though I was relating it to kinetic energy, energy of motion, we still think of this as energy stored inside of an inductor. So we think of it as stored potential energy. Yes. I was just relating what it is to kinetic energy. But if you think back to last semester, even kinetic energy, the way I tend to think of it still is energy stored in the state of motion. So it's still energy that is being stored somewhere. All right, now the new stuff that I wanted to introduce, but I wanted to make sure that we had a better foundation on what we were just talking about, is the idea of RL circuits. RL circuits being resistor inductor circuits, where you have a resistor and an inductor in the same system. So you have here an EMF with some sort of resistance between R1 and R, in which case, as the switch is over just this prong that's connected to E, the current is going to flow through the outermost loop here. And you get that as the switch is, or as the EMF is turned on, you're going to get that there is some sort of, how can I say it? There is some sort of ramp up here that we'll be able to measure in terms of the current inside of the inductor as a function of time. Because the back EMF meaning how much, if you think of it as being 9 volts EMF going from one side of the inductor to the other, so I get a 9-volt drop from here to here based off of a 9-volt EMF. What happens is as the current changes very quickly when you turn this on, you get a back EMF such that the net EMF across the inductor is not 9 volts, as you would hope, based off of this 9-volt inductor, but maybe it's 8 volts or 7 volts, depending on the change in current with respect to time, and L being the inductance. Okay, so you have a 9-volt EMF, but as you connect a voltmeter across the inductor here, you find that instead of 9 volts from the EMF here that you feel like you should measure, you end up getting 8 volts, and that would very quickly ramp up to the full 9 volts based off of this term right here. And you can go into your book and see the derivation for this, but the idea is that inductance allows us to relate currents to flux. We've already talked about that, and therefore changes in currents to self-induced EMF. As the current changes, there is produced this back EMF, that's what I've just stated on the previous slide, in the inductor that resists changes to the current. The net result is that it takes time to fully change the current in an inductor, okay? Again, it goes back to the idea that if you have increased mass, it is going to be more and more difficult to change the velocity of that system. Just like if you have more inductance, it's more difficult to change the current. And so, based off of an EMF inside of your system, a resistor inside of your system, or some equivalent resistance, and an inductor, we could use the loop rule from Kirchhoff, which is a conservation of what law? Kirchhoff's loop rule is based off of the conservation of what? Voltage, energy, more specifically. Voltage would be energy per charge. So this is more akin to a conservation of energy. So we apply the loop rule and we take the increased voltage from the EMF, the drop in potential that you would get inside of the resistor, and the additional drop in resistance, the drop in voltage based off of the change in current with respect to time. And what happens is that the current as an inductor is ramping up is equal to epsilon naught over R, not epsilon naught, E naught, the EMF over R, times 1 minus e to the minus t over tau. And in this case, tau, the time constant, is not RC, it is L divided by R. Inductance divided by resistance. Now, how is this different from a capacitor that was charging? How is this system where the current is ramping up in the inductor different than the current in a capacitor as it is charging, just based on the graph or your previous notes? If you go back in your notes and look for a capacitor that is charging in an RC circuit, you start with a very high current because it is very easy to stick charge on the capacitor, and it slowly ramps down to 0 as you fill the capacitor. So it is the mirror opposite in terms of reflected across, say, this axis here, this horizontal axis at my cursor. The current inside of a charging capacitor went as I times e to the minus tau. It wasn't 1 minus e to the minus t over tau. It was just I times e to the minus t over tau. So it is similar in nature, but instead of the current ramping down, we are slowly building the current up here inside of the inductor. And you can also measure the drop in current inside of an inductor. You turn off the power supply to the inductor. And what happens when you do so is that the current is going to slowly start decaying to where it eventually reaches 0. But it does not go to 0 immediately. Again, you imagine, based off of if a resistor is akin to friction, if I give a push on a block, what happens to the block when I stop pushing on it is its velocity is going to decrease, but it is not going to decrease immediately. It's going to be a function of the resistance and a function of the mass. Okay. Are there any questions before we give one or two problems a shot here? Yeah, so my upgraded version of Minty, I'm allowed to create my own templates now. And so I ended up just changing the logo, and this is actually based off of the UAH color scheme, like the approved marketing color scheme. So hooray us. All right. Thank you to whoever said they hope I feel better. All right, will there be any bears on the exam? There are at least 2 questions where something about bears is one of the answer choices. I'll go ahead and spill the beans. It's not the correct answer, but it is there. No, it is worth 0 points if you answer the answer regarding bears. 2 equations 2 days before the test is wild. Thank you. I appreciate your feedback. I would like to remind you what I said Thursday, that I feel like it is important for you to be aware of RL circuits, but this was not going to be on your homework and not going to be on the exam. It's just something that I feel like you need to know if you're an electrical engineer. So thank you for your feedback. Will Chapter 28 be on the exam? Yes, it will, up until I think it's 28.7 is the last section. I just covered 28.8, but that will not be on the exam. So 25 through 28.7 is on the exam. I just want to confirm, little n is the number of turns per length. Yes, that is correct. Little n is turns per length, where big N is total number of turns, and L would be, L is the length of the system. Is R in those last equations equal to the resistance of the circuit? Yes, it is. R is the resistance inside of the circuit. If I had just one night to study the material, what should you focus on? I can't imagine why you would ask that question since you started studying a week ago, but for whoever asked this question, if I had one night to study this, I would make sure to study the, let's see, I'm trying to even think of what's on this exam. What? Study your life choices, yeah. I don't know. I would focus a lot on Ampere's law and things along those nature. Why is sleep a scam? I don't know. Talk to our friends in psychology about that. On a scale from 1 to 10, 10 being the hardest, how hard is our exam tomorrow? 0. There is no exam tomorrow. Your exam is on Thursday. So the current going through the inductor is gradually increasing. Yes, as a function, if it's ramping up. When you connect the power supply. If you are disconnecting the power supply, then it would be gradually decreasing. Yes. In what scenario does current decrease for an RL circuit? If I go back several slides, there was what was called a make before break. I had to learn about this one. This is called a make before break switch. So if you allow the switch to go between the 2 prongs there, it allows the current to maintain its current state. But then if you go just towards F here, so go from D to F, what ends up happening is now there is no EMF connected in this loop here, and so the current would start to decrease. You have effectively disconnected the EMF, the power supply, and so in that case, the current would start to ramp down according to this rule right here. So that is how current decreases in an EMF. Should I pull an all-nighter to study? Absolutely not. Fun fact, if you talk to your friends from neuroscience or biology, if you are low on sleep, low on food, then one of the first areas of your brain to shut down is critical thinking, which is very, very important, you might have found, for a physics exam. So all-nighters are a terrible idea. Don't do it. In what scenario does the current, we already answered that. Is this test worse than the first one? I don't tend to think so. I say they're about the same. Do inductors add resistance? So what's the term? Not just resistance. Electrical engineers use it. I only use it like in one of my classes. What? Impedance, yes. So if you relate everything back to impedance, like resistance, then inductors do have an intrinsic impedance. So they are related, but and inductors are going to have resistance even if they're made of conductors, right? We said that resistance is equal to rho L over A, right? So resistance is rho, the resistivity, times L over A. You really have to use a long length of a conductor to get any sort of inductor. So there is going to be some related resistance, but it's not going to be usually as strong as an actual resistor. Okay. That's an existential question, and again, I would go to our friends in the philosophy department. Are the pre-lectures? I would think the pre-lectures are good in terms of the conceptual, what topics will be most heavy on the exam. There are 24 conceptual multiple choice questions I've written so far. There are 6 from each of the 4 chapters that we're covering, so I try to make sure it's pretty well distributed evenly across the material. If you know nothing else before the exam, you will be incredibly frustrated if you do not know how to use the right-hand rule for measuring where magnetic fields point based off of currents, or in what direction forces are based off of moving particles in magnetic fields. So those 2 major right-hand rules, if you can't do those, a lot of the conceptual multiple choice questions are going to be frustrating. So review that. Okay, y'all keep throwing questions at me, but we got to move on because I'm ready to sit down. There's the QR code if you need that. Flash that up there while I look for what problems we're supposed to be doing. So many problems. Again, these are all on Canvas. So if we don't get to all of them today, please see Canvas. I can tell I'm running low on steam anyway. For this one, we've got magnetic field strength. So this is B right here. B is equal to 0.8 Tesla. The rod has a speed of 10 meters per second. We'll call that V. And we said the resistance, according to this problem, is 2 ohms. Find the induced EMF in the circuit. Well, we have this guy right here, and we said that the induced EMF is equal to B times LV when the velocity and the magnetic field are constant. So the induced EMF is 0.8 times 0.2. Sorry, here's the length right here, so equals 0.2 meters. And we've got times 10, the velocity. This comes out to be equal to 1.6 volts. Part B, the induced current. Well, I know from Ohm's law that V is equal to IR, or that means that I is equal to V over R. The resistance is 2 ohms, so this comes out to be 0.8 amps. Or 800 milliamps. And then part C, the net force needed to move the rod at constant speed, assuming no friction. So how do we calculate the force required to move this thing to the right at constant speed? Does anybody have any ideas how we could figure out what the force needed is to pull this at constant speed? Rate of energy dissipation, that could be a way to do it. There's going to be a little bit more straightforward way to do it based off of something that we said way back in chapter 25 or 26. Yeah, so remember that the force is equal to IL cross B, right? So L is going to be, well, first of all, we need to determine that we're increasing the flux inside of this, so there is going to be an induced magnetic moment based off of this loop here, mu, that is going to be out of the page, since the magnetic field is into the page. And so the question is, in what direction does the current, sorry, that was really loud, the current need to be flowing around the square rectangular loop in order to induce a magnetic moment out of the page to counteract this increase in flux going into the page? In what direction is the current flowing? It's going to be going counterclockwise, yes. That the current is going to be going like so. Good. If you don't, yes, what? Okay, so if you need to be reminded on why it's counterclockwise, figure out the direction of your induced moment, that's B. So eventually your palm is going to have to point towards B. You choose any leg of your rectangle here. I'm going to look at this leg right here. So if I align my thumb to the current, the way that I get my palm pointing out is for the current to be going up. If the moment was into the board, then I would have had to move my thumb down, so that way I had a magnetic moment going into the board. But since the moment is out, my palm points out when I, along the right-hand side, have a current going up. Correct. That's a different right-hand rule. That's to figure out the force. I was just trying to figure out the direction of the current here. You align your thumb for the direction of the current, and then you reach out to the point that you're trying to measure to. So I'm reaching out to the left, and so my palm points out. That's going to be the direction of the induced moment. I didn't. I knew that the moment had to be out of the board. Yeah. I knew that the moment had to be out of the board. My palm had to point out of the board. Along the right-hand side, I have two options if I'm reaching out to the left, right? Correct? If I'm reaching out to the left, I have the option for the current to be going up on that right-hand side or going down, right? It's either up or down on the right-hand side. Well, I want the moment to be out of the screen, so I have to turn my hand like this to get the moment coming out of the screen. And now it comes to the right-hand rule that you were just asking. Okay, if we want V cross, or let's say IL cross B, well, in that case, you've got L is going to be pointed in this direction. So this is L hat. If I take L crossed into V, so now I align my middle finger to L, I cross into the board to get B. The force in this case is going to be to the left. So it is going to be a resistive force here. And so that's going to be equal to 0.8 amps times a length of 0.2 meter times a magnetic field strength of 0.8 Tesla, which is 128 millinewtons. Yes, Bill. How did I know the moment was pointing out of the screen? Good question. How did I know the moment was pointing out of the screen? According to Lenz's law, the induced moment opposes the change in flux. Okay? Opposes the change in magnetic flux. The magnetic flux is increasing going into the screen. And if I'm opposing that increase into the screen, it means I have to induce a moment out of the screen. Yes. The speed, we did have to the speed gave us the induced EMF right here. So it does matter. In fact, one of the things that you could do is you could go back and look at my solution, in which case I find the force related to each of the values given to us, and the force is equal to B squared L squared V over the resistance R. So as you increase V, you linearly increase the amount of force you need to pull it at that constant speed. All right, I would love to at least do one of these that has inductance, but I really want to sit down. I don't know. I'm debating on it. I really don't want to do office hours today, but I might do it and just sit there and we'll see. I'll go up there at least. When the current in an 8, this would be L, the inductance, 8 Henry coil is equal to 3 amps and is increasing at 200 amps per second. It's pretty impressive. Find the magnetic flux through the inductor, through the coil, and the induced EMF in the coil. Right? So the flux, we said, is equal to L times I. That was the whole point of doing this. So it's just 8 times 3, so 24, and that would be Tesla meters squared. That's part A, so this is not a difficult one, I recognize that. And part B, the induced EMF in the coil. We said induced EMF is equal to minus d phi dt. The inductance is constant. So that's minus L di dt. And this is going to be di dt. I think that's what I meant to write here. So that's going to be minus 1,600 volts, or minus 1.6 kilovolts. You have an inductance of 8, so this would be equal to 8 times 200 amps per second. 8 Henry times 200 amps per second equals 1,600. Yeah, d/dt, right? Yeah. So what tends to happen on the exam is I ask something like this. I haven't actually written your numerical questions yet. That's what I'm going to do today. And one of the things I ask you about is something almost exactly related to this question. But I don't care about the flux. We never really care about the flux. We always care about the change in flux. And so what I'm trying to get at is, if part A was not there, the fact that the current was currently 3 amps would mean nothing. That we don't care what it is at any particular time, we only care how it's changing. Okay? All right, we're not getting out of here as early as I thought we would. Y'all work on your practice exams. I'm going to open up the clicker if you brought your clicker. I'll float around and do my best to help you guys, and then we'll be good from there. We'll go over it before I leave today. So you can leave if you want to. You can stick around if you want to. But in about 20 minutes, I will go over the answers to the practice test. If you didn't get one, there are several copies up here still. But your clickers should be open at this point. Your ID is everything before your @ symbol on your email address.
So, question number 6, you said current is carrying, wires carrying current into the center of the page. So, you saying center like this or like this?
No, it's going into
Into the page like this? So, it's going to be going.
Yeah, so you imagine a wire that is
So,
doing
the wire
this.
is doing this, and then if it's going in, that goes right here. So, it's not really much.
So you go like this, and then you go out to this point right here.
So, it's going out to that point right there. So, it's
Yeah,
going like
so
that.
if you align here and you reach out to the right, the magnetic field will be going down. All right, see y'all.
Wait. So
You put your current in the direction of the thumb.
Current is the thumb. Okay.
Yeah.
Gotcha.
You reach out to the point over here to the right.
Yes.
Your palm points in the direction of the magnetic field.
Okay. And it goes this way. Okay.
It goes down.
Down. Gotcha.
Yep.
All right. Cool. Thank you.
No problem.
I was just confused about that one.
Channel 12. Yes. Oh, yeah. Wrong equation sheet. That's why it says 1, exam 2 equation sheet. So pull up on campus if you want the equation sheet. Sorry about that. What's that?
Just had a quick question about one of these formulas.
Okay.
So I was working the homework last night, finding these L's inductance, right? It seemed like the correct answer was this, but it was divided by L.
I think you're right. I think I have an issue on that one.
Okay.
Let me mark that so that way I can fix it when I go
'Cause-
back to my
N
But
is
if you
N
look at the
divided by L.
slide, I know the slide is correct.
The slide.
Yeah, so if you go back to, if you, here, let's just do that. Maybe you were given the total number of turns?
Oh, I'm confusing big N and little n.
Yeah.
Okay, cool.
Yeah.
Thank you.
No problem. Hey, what's up?
I will not be here for this test either.
Okay.
I have a flight Thursday at 6:30 in the morning out of Huntsville to Portland, Oregon for a commander's conference.
Yeah.
So-
Will you be in town on Monday?
Yes.
Okay,
Yeah,
we'll
I'll
do
get
it on
back
Monday.
Sunday night.
Okay, we'll do it Monday.
Okay. Do you want me to send you like my itinerary? I know this is like the fourth test that I've missed. I don't want you to think that I want to skip it.
Yeah, if you don't mind sending
Yeah,
it to
I
me,
can do
that'd
that.
be fine.
Okay,
Yeah,
thank you.
Absolutely.